Hey everybody, welcome to the stream. It's another Sunday. I have started a new thread on the Discord to track these streams separately from the essentials of compilation because we're, going off in a different direction. Um, and I think it's worth having a new sharing thread so people can talk about things. Anyway, thanks for joining me last week. I had a pretty good time. And I was reminded of the challenges um, that this sort of thing uh, entails, and I think that um, we have a long road ahead of us. Hopefully, what will happen is as we get better at this, both the like generating code and like thinking about the problem, it'll get easier. Um, that's my hope at least. So we've got plenty to do today, um, and I think that the place that we're going to start is we kind of did a very basic um, wrapper generation, but today we're going to do some things a little bit differently. Um, we're going to, first of all, generate the rest of the wrapper. So we generated like one function, right? Hello, Renathias. Okay, so we generated one function, but we didn't have the rest of the forms that are required for an actual Erlang module. So I'd like to finish that. We have to, for now we'll fill it with some bogus data, but um, as we get this closer to ready to generate really good parsers, we'll have to thread more information through. And I think that one of the things that was good about the form and essentials of compilation is that for every stage we had an IR, an intermediate representation, and we kept all of the bookkeeping stuff that we needed in that. And that's something that we'll need to do here. In our first pass, we're being very, very minimal. We're not really even building a whole IR. Um, we have, a grammar, but it doesn't have any information about the mechanics of the parser it's supposed to generate. It just has like the rules. So um, we're going to finish generating that wrapper. Um, and then we're going to add a new, hopefully we'll get to adding a new terminal that we can recognize. And the most obvious one um, is very simple, but it also introduces some new things that will be kind of interesting. So let's get to it. And welcome again to the stream. So, okay, so where we were last time, we had this thing and this functionized rules. It took the grammar and it basically turned this into like, here's the syntax tree, which is, Erlang terms. Like this is Erlang syntax uh, for for this rule, and this is a function. So it's going to generate a function. And then in our generate wrapper, we just went and said, hey, take this this name of this function, create an atom for the name of the function, give it a variable, right? Um, as its sole argument, and then generate a function for it. So basically, we get a list. Uh, given this list of function name to syntax tree, we get a list of functions in the abstract syntax, the Erlang abstract syntax. And then we turn it into a form list. So form list is, just to take a step back, Erlang has two kinds of syntactic constructs. They're expressions. So those are the things that you would think of, like are the on the inside of a function, like on the body of a function. Um, and you have forms. Um, you also have expression lists because the Erlang syntax, of course, allows side effects, or rather, you might have one, I guess you could call it statement. They're not really statements because they still return values, but you could say something like, A equals this thing on the right, and that's an expression in itself. The thing on the right hand side of the equal sign is an expression as well. But then you have, a bunch of things, and then at the bottom, your return value from the function is like a plus b. Okay, so that is an expression list, or sequence, and then when you put a function header on it, so a function being a sequence of clauses, this is important. Notice we create a clause here. A clause contains a sequence of expressions and a header. So like you can, the interesting thing about this, and I don't know if any of you have done Elixir, but you can basically treat in Erlang and in Elixir, you can't do this in Gleam for good reasons, but you can treat a function as a case expression, basically. And that's why it uses the same form as a case expression. So this, it's interesting, we did this bit earlier. We were generating this. We could have inlined this into the function header. So let me do that so you can see what that looks like. And we're not going to generate this code. But this is basically what it would look like. And note that I use a semicolon. Semicolon is between clauses that are at the same level, right? We could have written the function like this. But we didn't. We wrote it like this. And I think that this is probably generally better, especially because we will likely want to introduce fresh variables. Like this rest is static here, but we'll probably want to have a variable name generator, because we'll eventually be doing continuation passing on this stuff when we get to sequences. But okay, to get back to it. So once you have a function with all of its clauses is a form. And forms are all the top level things in a module. So, and you have basically three kinds. You have functions, of course. You have attributes. I say there's three, but it's more like two. You have attributes, which if you look up here, things like module. So declaring the module name, declaring the exports. Those are attributes. And then you have types and specifications. These specs are actually also attributes. They're just not typically written with the parentheses, right? So we need to generate, getting back to where we need to generate at least this stuff. Maybe the spec we leave out. We'll see. But at the very least, we need to generate the module name, the exports, which are going to be basically static templates, similar to how in the essentials of compilation, we would generate some code for every function with some slight variations based on how many stack positions were going to be used, etc. And which arguments the functions took. But you would generate, you need to push these things on the stack. You need to set the base pointer. You need to align the stack, and then you jump to the actual code. This is the same sort of thing we're doing here, but we're going to do it with Erlang forms. Okay, so let's generate, first let's generate this function. We're going to generate a string entry point. Okay, and then this is going to take an argument of what is the first rule in the grammar. So the convention that it's not always the case. Often, what happens in other types of grammar specifications, you say what the root symbol is. In Neotoma, you just put it at the top of the file. That's the first thing that. So I'm gonna say this is root. Sorry, I'm getting my languages mixed up here. Root is a string, and we're gonna get a syntax tree. So we're going to generate that whole function. And then let's make a function which is generate module attributes. And this is, we're going to give it a module name. This is going to be a string. Except this is going to be a list of syntax trees, because what we want here is, we're going to have multiple attributes. So what we want here is, module and then the exports. Let's do that one first, because I think that's the simplest. So, okay. We're going to, mod name is going to be syntax Atom create module name. Okay, and then we're going to, we need to make atoms for all of these things. And this is actually a place where I feel like I would really love to have constants for these sorts of things, because they're going to be reused a lot. But there's not a way in Gleam to directly say this thing is an atom, like as a syntactic form. You have to do this, atom creation bit. Module, and we're going to say export is atom create export. And we're going to say string is atom create string. Okay, so let's build up the forms. So the first one is going to be, and we need to look at the docs just so you can be clear. There's these attribute constructors. So let's look at this. Attribute takes a syntax tree and either takes none or a list of syntax trees. So if arguments is A1 through AN, the result represents, so the first argument being name, dash name, and then the list of arguments. If arguments is none, it results in dash name dot. The latter form makes it possible to represent preprocessor directives such as ndif. Right, so this is if we are using the preprocessor in Erlang, we'll want like if def, ndif stuff. And the ndif has no arguments, so you have to be able to represent it. In this form, in our current goal, we're not doing that. So we just need to make this an empty list if we're not going to pass anything. But in both of these cases, these attributes need to be lists. So let's say syntax.attribute. This doesn't exist yet, so we're gonna create it. Okay, so we want to create the module. So it's the name is going to be module, and the arguments is going to be mod name. Okay, and then the other one is going to be a bit more complicated. The attribute is going to be export, right? So we created this atom, but actually we need to wrap these because they need to be syntactical atoms, not literals. Okay. All right, and we're going to need arity qualifier. So this is body slash arity, right? Okay, so we're going to make the export attribute, and it's going to have syntax arity qualifier. And I think we'll just use abstract there. I don't think that there's not an integer literal, or is there a number literal constructor? I don't think so. I think it's we just use abstract, which is fine. Well, there's integer. I don't know what the... Let's just assume that it's there. I don't know what the difference here is. Let's look at the code. That'll be fun. Okay, it just says tree integer. Well, it might be useful is, okay, no symbol outline. Let's look for abstract. Okay, so yeah, abstract just calls integer. So like this is the quick way. If we have and by the way, this little bit here is why we got in that test, we got this rather than the string. Interesting. Because we did, you know, abstract rather than calling, hey, construct a binary. Okay, let's, rather than import that, because it just calls integer when the argument is an integer. Yeah. Yeah, there's a lot of internals here. We'll get familiar with, probably more familiar with it than we would like. All right, so let's go over here and we're going to define those things that we're missing. Okay, external Erlang Perl syntax attribute. Oops. Attribute. This takes a name, which is a syntax tree, and we don't have a way to specify none. So probably what we'll do is we'll make a form if we need that for preprocessor directives. We'll make a form that just takes no arguments. Okay, and that's all we have to do for that. Then we need the arity qualifier. One thing that occurred to me here as I was thinking about what we were going to do today is we need probably, this is all generating valid or trying to generate valid syntax trees using a built-in module that comes with OTP. But we're probably going to need a form sort of like the x86 assembler. Hello, Anna Abel. Welcome. Um, we're kind of going to need something that looks like the x86 assembly that we had in Essentials of Compilation, but has things that assembly doesn't have, like variables or abstract instructions. We're probably going to need something that's just slightly above this level um, pretty soon. Okay, so this is going to be, what do they call it in the arity qualifier? Body arity. Okay, so body is a syntax tree, arity is a syntax tree, and it returns a syntax tree. Okay, so now we've got the module attributes. Let's do the string function, which should be straightforward at this point. We've already generated functions like this. So let's just copy this bit. So the root is going to be root rule is going to be syntax atom create root. Okay. And then we will generate a function. So let me paste this. It's going to be create string. No, we're kind of doing this in multiple places. That bit sucks. Okay, and then so we're creating a clause which takes the variable input, and then we are going to do application. So this is a abstract application expression. All right, so we're going to have to do that. And I'm going to call this a local application because we're going to need to be able to call other modules as well. And I'd rather that be the more canonical one. So but ultimately what I'd love to do is yeah, turn this rather than kind of building all of this at the last moment. I would rather us kind of build up an abstract version of this where we have like a module type perhaps and we make definitions in that module and then those definitions contain Gleam side abstract syntax, and then the flattening of that into Erlang abstract syntax is a very mechanical, like case-driven, recursive thing. That's what I would prefer in the long run. Okay, so this is, oops, what do we call this? Operator is a syntax tree. Arguments is a syntax tree. And that returns a syntax tree. Okay. So we're going to do a local application of root rule and the variable input. Okay. And then finally, we do the same thing we did up here, right? So let's do that. Okay. So let's just get rid of that. Let me turn that into a non-piped, right? Okay, so now we have let's take we're going to generate module attributes, and for now we're going to say it's just G. We don't have we don't have the information about what the module name should be called. Ultimately, it should be called whatever the input file is, or whatever was passed as an argument to the tool when we generate the parser, right? Okay, so then we're going to append. So let's get okay, so we've got the root rule as a string. So we're going to generate string entry point, passing root rule. And then we're going to take all the functions that we generated by processing all the rules. And then we're going to pass that to form list. And here, I think we reach another stopping point. So what we're going to do is we're going to run not this, but our test program. So we have a simple grammar. It has one rule. The name is G. So this is basically we're reproducing this, right? The only thing we haven't put in there is spec. And I think I'm going to leave that out because we might want to change this contract, right? Okay, and it matches an expression, which is a terminal, which is a kind of a static string. And then this is just, span information about where it came from the input grammar. Okay, then we're going to pass through our two phases. We're going to format it and then do print line. Okay, so I've got a problem here, and this is in my syntax file. So this is list of syntax tree. No, not arity qualifier. Application is a list of syntax tree. Okay, so cool. We did it, fam. All right, we did it, chat. So we have a module, and the thing is in Erlang, the order matters on this. The module declaration must be the first thing in the file of syntax. It's not comments. Now we have another problem here. This is wrong. So let's fix that. This is correct. This is correct as it was before, what we did last week. Now we just need to fix that export. So we have so rather than a direct thing, we have an abstract list. Okay, so right, so this lets you, similar to how we have the splat in Gleam, this is a cons expression, but if you have none, then it just creates an empty list, right? So what we will do is we'll make this one. And we'll call that other one a cons. Like this version of this function will be like list cons or something like that. So it's more explicit. And I think my split is getting out of control here. So let's at least hide the shell. Okay, so we need list one. Yeah, it just says a list, or say a list of syntax tree, and this returns a syntax tree. And then we will I'm going to put a note here, use list cons 2 for head tail constructions. Okay, create. Okay, when we need that. Again, I'm not trying to create a whole Erlang abstract syntax library for Gleam. I just want to create the stuff that we need to accomplish our parser generator. Okay, so now that we have this, I can go back over to here. So our attribute needs to be actually make another list. And this is going to be syntax.list. And let's see what we get there. Okay, so now that construction is correct. If we add other functions, which we will eventually, we'll have a function which is read a file, right? Then yeah. So we generated Erlang code. Okay. Let's clean up this. We might want to make some tests. But let's make a quick commit. Okay, so we're going to say this is episode 2. Generate the rest of the Erlang module. Okay. Okay, so going back to our grammar, we have a lot of stuff here. A lot of stuff that we didn't implement. And in fact, even this, like, we have rules and grammar is a list of rules. That like doesn't really do anything right now because we've only defined a grammar with one thing and we don't have a way to have non-terminal expressions yet. So what we're going to do is we're going to add one more terminal, and I think it's going to be this anything terminal. So this is the dot operator. Okay. This will match, and here's where we need to make some pretty critical decisions, I think. The goal of this is to match any single character. Wow, that sounds pretty easy. Well, welcome to the modern era where not everything is in ASCII. Not everything is even UTF-8. We need to make some decisions about what we are allowing this to be. So I think, given that there are lots of text encodings, and I'm not, this tool is not designed to parse binary. Like, I think that there's really well-established techniques for parsing binary, and you don't generally reach for a grammar to parse binary files. if you're doing that, you want a different tool, I think. So what we're focused on here is text, things that humans can read. Um, and for that, I think we need to look at what are the potential qualifiers for recognizing a single character. Um, Now we can, let's see if not that. It's probably in the reference manual. All right. Character sets and source file encoding. So Erlang, being originally written in Europe, um, it uses a form of an 8-bit encoding called Latin 1 or ISO 8859-1. You can think of it like ASCII, which is 7 bits, not 8. Um, but the other bit is used for characters with accents and a few other things. However, um, recently it got support for Unicode literals. So you can set the source encoding of the file that you expect. Note that in Erlang 17 they switched from the default was changed from Latin 1 to UTF-8. Now I think that that's important for us for our generated code. I think we probably want to say when we generate a file, yeah, the default is UTF-8, but we probably want to specify it via a comment at the top. Yeah. So if we look at, let's see here, pattern matching. Yeah, let's see, not efficiency guide, interoperability. Where's the thing on binary pattern matching? Functions, expressions. Here we go. Bit syntax expressions. So bit syntax operates on bit strings. A bit string is a sequence of bits ordered from most significant to least significant. So the empty bit string, 0 length. So the reason why I'm reaching for this is, if you did not know, strings in Gleam are bit strings in Erlang because they contain characters that are outside of the Latin 1. They're actually, it's that you can think of this construction as a list of bytes. But you can have these specifiers on it, so you could say that it's actually fewer bits than a byte if you wanted to extract a particular field or construct one. Okay, so we're in the right area now. So this slash binary just says, hey, concatenate two binaries together, this thing. Except they're just showing here that this is wrong because you haven't specified how many bytes to consume. But in this case, you're saying, hey, consume 3 bytes. All right, I want to get down here. Okay, so we can say integer. What would be relevant for characters? Integer, if it's between 0 and 255, right? Because that's 1 byte. Or we can say it's a UTF-8 character, which puts a little bit of onus on the pattern matcher in that if you have a character that's outside, it's greater than 127 in its numerical value, then the UTF-8 bit is carrying a lot. UTF-16 and 32 are fixed width characters, though. So if we wanted to support those, that's pretty straightforward. Now, the other thing that brings up is it's possible that this string, we should also have an encoding attached to it. For now, I think that we should assume UTF-8, and then we should plan to allow a grammar writer to support different encodings, either in their like as an attribute on their grammar, or like as an argument to um, to the invocation of the parser. So that might mean that we might need to specialize things that recognize terminals into multiple versions. Ones which recognize UTF-8, ones that recognize 16, and one that recognize 32. Maybe that's an option that we give later. I think for now, and for backwards compatibility's sake, let's just say that they are UTF-8. Terminals are in UTF-8 encoding. So note that UTF-8 encompasses ASCII. So if you're all of your bytes are less than 127, you're fine. Less than or equal to 127, you're fine. If they are greater than, then we have to assume UTF-8 encoding. And if we want to later support other encodings, so one thing, when I said we'll have to create a version for each of these, it's basically like we're doing monomorphization over a generic, right? The encoding will need to be specified at grammar definition time or runtime invocation or invocation of the parse. If we support multiple encodings at runtime, I think it gets more complicated. I almost want to say the whole world is using UTF-8, but I have a very narrow view of the world. So if it's not, let me know. It is very common, partly because it's just a simple and ingenious encoding. But there are ambiguities in Unicode in general. Like you can have the same glyph being represented by different sequences of bytes, which is kind of problematic. So I'm going to say the latter being much more complicated. The other thing here is that this, if you want to support more than one encoding, it might actually explode the size of the module by a factor of n for how many, where n is the number of encodings. We might have to make rules that are suffix, like this one is UTF-8, this one is UTF-16, this one is UTF-32, right? Okay. Little divergence there. So what I want to go do here is, now that we have defined this particular terminal, and the whole reason I went down that tangent is we need to add a pattern for it here. All right. Okay, so we're going to say match anything. Let's make, so we're going to have to do something similar to this literal string. But it's going to look quite a bit different. And we may have to introduce our, fresh variable thing, which will mean that we need to, well, let's not do it yet. let's say we want to match anything. And this is going to return a syntax tree. And it's going to be a clause, right? It's interesting here that we have this this failure thing. We're going to have to repeat a lot of this. Okay, and then finally we're going to do syntax, case, expression, variable. And here, since we only allow, eventually this will have to be threaded through, we'll do continuation passing style, but since we only allow one terminal in each rule, we have to just like statically put this in here. This is actually wrong. We want to thread in like what's the incoming variable that holds the current stream of characters, and then we would also want to take, like in this case, if we match a single string and this has a continuation, we'd be passing here's the remainder, like, well, here's the value we parsed and the remainder of the input stream as a variable, and like these would be creating fresh variables each time, and we'd have some structure that tracks that for us, so we generate unique ones. Okay. We did a lot of that in Essentials of Compilation for generating fresh variables, right? And generating like names like of blocks and such. Okay, so we have success clause and failure clause. Okay, so we know this has to be syntax tree. We're not matching a literal string anymore. We are going to I need to go back to the okay. So binary field, right? So this one takes. We already probably did a binary field with types. Yep, binary field with types. So we're gonna say encoding equals syntax Adam create UTF-8. Okay, not 7. Okay, so that's gonna be our encoding. And we need to match it into a variable. Syntax variable. And we're gonna say not Adam create. Syntax variable, and we're gonna say char as the character, right? And then the pattern. All right, so we also need to do this. Let's copy that in there. And then we're going to do that. Okay, except it's not going to be this. So we need to make, the literal was this binary. The thing is, when you pattern match out this character, okay, so we're going to say result is going to be a syntax binary, which is a syntax binary field with types, and that's going to be variable and encoding. right? Okay, but this is also going to be the pattern, so, or part of the pattern. So I think that we need to say let variable field this. Okay, so we've got, this is the result that we're passing on. So here, the pattern is going to be variable field. The result is going to be tuple variable field. Except that needs to be wrapped in a binary. So we're pulling out this character, but we don't want it to go into whatever comes next as a bare character. We want it to be a binary. Okay. Oh, we already did that. So let's say result. Okay. So this is match anything. Let's go over here and see what happens if we change this to anything. Okay. So yeah, it's just complaining we didn't import that. So what do we get? Okay, so we still got the wrapper. Our rule has match on input. This variable is a UTF-8 character. And the rest is a binary. And then we say, okay. And we return that character back in a binary. And the rest. This is exactly what we wanted. So we've done one more. All right. I think that somewhere here, and I'm going to pull this off screen just to be sure. Somewhere here I have downloaded the the is it under this? Might just have to search for it. All right, if I haven't, then we'll just go look for it on the web because it should be freely available. Let me dig one more minute, and then we'll go to the web to pull it down. Oh, that's not it. Okay. Yeah, I don't think it's in here. Hmm. I think that this is. Yep. All right. We will go to the web. So what we're looking for here is Brian Ford is the author of this research, parsing expression grammars. Unfortunately, he has a very common name. Okay, so we can look at papers, theses. His Here's the one. Yeah, see, I have downloaded it. It's from 2002. This is the web page you should care about. Here we go. PDF. It's just called thesis.pdf. Do I not have that? Downloads thesis.pdf. It's weird that it's referred to my project, but it's not in here. Okay. um, you can see clearly I have downloaded it. So we're gonna save link as, and I'm gonna put it in. Yeah, downloads is fine. All right. Yeah, it's not even in my recents. So downloads, we've got fine. Thesis.pdf. There we go. Okay. The other thing that we'll want to look at is go way back to his like stuff that came before it. So there's this paper, these two papers actually. Um, okay, so that's actually his thesis. This one, um, let's go ahead and download that, and it's functional Perl. So download that. Okay. There should be another thing in his works about, yeah, this one. Okay, this is another thing that we can use. The thesis is, I think, more authoritative, but clearly this came after the thesis, which is listed as 2002. And so there's possibly some things in here that we'll want to, make use of. Specifically, our concrete syntax for our parser, our grammar definition is going to look a lot like this, right? And we will use the definition of a peg, parsing expression grammar in here. So there are also, I think, some follow-up things about transforming left recursion that are interesting. You might want to look at. I don't know that he does any of that. There are other people who follow up on it. Okay, yeah, grammar. Let's just, okay, parse. Yeah, just those three. Recursion. Mm-mm. Okay, so there's stuff that he's done more recently that is not related. So, okay, um, good enough. Let's look at his thesis. So we're gonna have to like. This is not a step-by-step manual in the way that, hello Kythera, welcome to the stream. I'm sorry I didn't see your message sooner. This is not an implementation manual in the same way that Essentials of Compilation is. So we're going to have to, yeah, there's no table of contents in this. So we're going to have to jump to the things that are most important. Now here's the table of contents, doesn't link. This is how old this PDF is. Okay. So, page 24 left recursion is something that we need to not allow. Okay, and then there's parser generator for Haskell. This is the interesting stuff that we'll be adapting, I think. So if we go to page 59, let's just scroll down. Okay, so this is, they say it's based on TDPL. I don't think in this thesis he calls it parsing expression grammars, but you can think of it as that. And strictly speaking, it is a superset of regular expressions. But here's the grammar that he uses for this project in Haskell called Pappy. Um, okay, so you have space, a grammar, and the end file. You have ways to specify identifiers. Um, Identifiers are a letter or an underscore, and then letter, digit, or single quote. I'm guessing that's so you can have very common in Haskell and is this tick for prime. Haskell and OCaml love this. Hello, I am a random guy. Quick question: what is this about, and what is this? Welcome to the stream. Thanks for joining. Um, we are in the second episode of this series I'm doing on my stream. We are generating parsers from grammars. Ideally, we're using the programming language Gleam, and our target language is Erlang. So we are taking we're actually going to have three languages. We're going to also have the language of the grammar. So we're going to have a grammar. We're going to parse that grammar into Gleam data structures, and we're going to turn those Gleam data structures through a series of transformations into Erlang code. And then the goal of that Erlang code is to recognize the language defined by the grammar we first read. So that's what we're doing. I have an existing project that does this in Erlang, but it's got problems, and we're trying to start over to resolve some of those problems and use some things that we learned on my previous series about going through the essentials of compilation book. So that's the gist of what we're doing. Welcome to the stream. I hope you can continue to come. Okay, some idiosyncrasies of this grammar. Obviously, we have character literals and string literals. We may not want to support that. I don't think that I did in the original Neotoma. I think I said, well, you can use single quotes or double quotes for strings. If you do double quoted, then, obviously our negative look ahead says, hey, it can't be a double quote. And then there are aspects of, escape codes and such, right? Okay. And then, spacing is space character line comments. We had a different kind of comment in the original that looked a lot more like Erlang. That sounds too cool. I don't know. It's actually kind of nerdy, but I appreciate you. Okay. Space characters, an empty, like an actual space, or a tab or carriage return line feed. Line terminators are a combination of carriage return line feed or a single carriage return or a single line feed. And again, this is using ordered choice. So this being greedy means that it's going to try to match both first. If that fails, it'll try to match that. If that fails, it'll try to match just that. And then in file is just a special, there is no character. Okay. Note that there are things left out here. Where's this definition of what a character is? Right? I think it has to be dot. This is the any character. Okay. What I want to find here. Okay, so this is like this is the basic lexical elements, but you note that it jumps from start, which is the start rule, and it has grammar, and grammar is not defined here. So these are like the low level. I want to say terminals. They're not terminals. Like these things on the right hand side are terminals in some of them. But these are likely things that you would consider terminals, right? If you were doing a traditional lexer parser combo, you would probably have most of these things handled by your lexer. That's what this section is. So you would do something like create a regular expression which specifies what an identifier can be, right? Okay. Going down, this is where it gets interesting. So there's Haskell code blocks, how they can be embedded. We'll need to have something for Erlang code blocks. Um, yeah. So I think that we can skip over that. Let's look at this, the greater structure. Okay, here's the money. A grammar has a header, some optional raw code, whatever the top symbol is. We in the original Neotoma we didn't specify that. A series of definitions and then some trailer raw code. Okay, so the header is we're saying a parser, and here's a name, and here's colon. So parser, and then an identifier, which is the name of the grammar, and then colon. We don't specify that in Neotoma. Top says what is the entry point rule. We're not specifying that. Okay. Um, and then colon, comma. Those are sort of lexical level elements, but they're used here. And then non-terminal definitions. So this is where it gets a little bit funky, and we'll need to make some decisions about this. There are aspects of the way I did it originally where the code block always comes after all choices, but Pappy allows you to put a code block in line with a choice, an alternative. So we'll have to see about that. Okay, so a definition, this is like a rule in your grammar, is a non-terminal, in their case, a double colon, the Haskell type. So this is, unit is the type, equals rule. We did something that looks more like this. Non-terminal, left arrow, and then an expression. Okay. Yeah. The reason they do this is because this looks a lot like Haskell syntax. The colon is used to define, to specify, or to separate, an identifier from its type annotation. But we're not doing that. Okay, and then let's go down here. Okay, so this is the core of the grammar rules. There's the primary rule, which is either a non-terminal or a character literal or a string literal, or open parens and then a rule and close parens. Okay, so they're enforcing parens around a sequence or alternation, which is interesting. Okay, so a rule is an alt rule, which is a series of sequences separated by slashes. So alt rule, so basically rules is always a choice. Excuse me. And that means that in this case, if you have only one alternative, then you get a choice with one in it. That's what their grammar says. And then a sequence rule is either a sequence, which I don't see that defined. I'm guessing that's, yeah, we'll see. Or a unary rule. And a unary rule is one of these primitives, or primaries, I think, with some potential decorator on it. So question mark, optional look ahead, star, 0 or more repetition plus 1 or more repetition, or it's just a plain primary, right? Okay, so sequence, it's interesting that's omitted. Okay, no, it's down below. Okay, mentioned to join and is not directly because it provides no indication of how a semantic result for the sequence is being computed from the semantic results of the individual components. Okay, so we'll need to see an example of this, I think. But they're saying that they use the right arrow. Right-hand side is a result expression. So a sequence is a series of matchers and an arrow pointing to a result. So this is sort of like defining a clause of a function, right? And then their matchers are identifier, So this is like, this is a binding. This is like, hey, given this unary rule, which we already saw up here is one of these things, there's an identifier in front of it. And that's the, when you get to this, you know, seek result, this is code, or just extract this identifier, right? So this is a binding for to be used inside this piece of code. Okay, and then there's raw code, which I'm guessing is like process this thing directly. Or there's a character literal or a string literal. We're gonna have to see example of this. So we'll look at it below. And there's and. So and is the positive look ahead. Not is negative look ahead. Yeah. Okay. So let's look. Here's an example. So exponent part. They're saying the type of this rule, so the return type of this rule is an integer. Okay, and an integer is either lowercase or uppercase e. So this is the exponent part of a floating point number, right? So lowercase or uppercase e, and minus, and then there's this digits thing. So v, this digits is some other rule in their grammar. And then when you get this alternative, you map it into this piece of code. So you say you bound v, right, is an identifier, and you have colon a unary rule. So they're showing this bit, and that means that inside this block here, this v is bound to the result of processing that rule. So we may want to do something like this. This is actually really good in comparison to what I had before. And I'm sorry, I keep going down this. We're like, hey, let's, I don't know, let's recognize some more stuff. Okay, so what I wanted to get to is, we need to think about what are the data structures we will use to represent this stuff, right? And maybe we can type out some of them today. But we also want to be able to recognize some other kinds of things. So we already added the anything, which you can see here, it just matches a character. And we return that character. And then any remainder. But the other things that we had in Neotoma were character classes. And we did have straight up regular expressions. Yeah. So regular expression would be this hash mark and then a quoted string. So in your grammar, it would look like, you know, either single quote or double quote, and you might say something like, variable, and then 0 to 9 plus, right? And that would match things that like variable 1 or variable, right? Except with only numbers. So that is a thing that we might want to support. Character classes were always this open square brace, and a sequence of characters that were either a literal escape of the slash or an escape of one character, or just anything else. And then it was like we passed it through the unescaper. So, and this character class was a structure. No, this is a a refactor version where I was trying to be more principled about it, but the original didn't do this. It was much sloppier. So I think excuse me, what might be interesting is um, to do something where we introduce an IR which has, or rather, this is sort of like remove complex operands. It was in Essentials of Compilation. Let's make character classes, right? And let's make a pass which turns character classes into um, a set of alternatives, right? Okay. So here we go. We're going to make a character class, terminal kind. Um, and then we will make a part of this which is going to panic. Character classes should have been expanded. So we're going to have it, and I think that they don't do this necessarily in. There's some discussion in here about um, reducing parsers. I think it had to do with they don't have character classes in Pappy, but there was some stuff where rewriting iterative rules. Yeah. Some stuff about optimizations. Like these things are kind of those are kind of interesting. I'm trying to find, there was a bit where so there's these transformations they do. So simplification, the people optimizer is like redundant sequences containing only one component, right? So we'll probably have an IR that removes, maybe even we will have a pass that removes sequence operators that have only one component, and choice operators with only one alternative. Right. So stuff like this, where you have parens around an expression that is the same kind as the outer expression, that gets rewritten to flattening. Oh, right. So they're saying on lexical analysis, it detects and left factors constructs consisting of a choice between several literal characters. Right. So if you have this, and we may need to do this optimization, if you have something where they have simple prefixes or shared prefixes, you would rewrite it to match that and then match that, or nothing. So we'll be introducing potential epsilon productions. Um, Epsilon meaning the empty stream, right? And what this looks like, and you can see here is, and we'll be generating code that kind of looks like this, um, which is, you know, do nested case things and have a, you know, a match here where if you get, you know, an opening right angle and then another, you know, and so forth, then, you know, on this case, then you have, if you have an equals following it, then you get this operator. If you don't have an equals following it, you get this operator. And this is that epsilon thingy with prefixes. There's redundant rule elimination, inlining. Uh, right. So they often have many non-terminals that have simple non-recursive definitions. Um, so those can be inlined. So folding copies their definition directly into their call points in the grammar. So there's lots of interesting things we can do here. If we have an abstract form, which helps. So let's go back to the thing with character classes. Um, I want to say there is going to be what am I want? What do I want to say? The character class is going to have some characters in it, obviously, which is a list of we'll call it character class entries. Um, and we will need to be a little careful because you could have a character class with nothing that matches. Um, but that's something that we can validate at the top level. If you give me an empty square bracket thing, I'm going to tell you you're bonkers. Okay. And this is literal string. And this is character class matcher. And the reason that we had these is it's just less noisy to define a character class than to specify a bunch of alternatives of individual characters that are literals. You know, A to Z, 0 to 9, like that sort of thing. Underscore. So this is going to be a single character is going to be a string, or it's going to be a character range, which is a start string and an end string, and those will be individual characters. But there's no. Yeah, I mean, we could use ints, but I don't think that that's what we want. So what we can do is, and this is where we're going to need to expand expressions. And it's why I brought up all that stuff about the metagrammar, which is what I'm going to call it from now on. The grammar for the grammar. And I need to go back up here where they have. Right, this is the. Oh, that's wild. Sorry. Okay, so if we look at this, an alternate rule is a sequence rule slash some other sequence rule. The only thing that we have right now is literals. So we don't need to do this, but we should go ahead and make these structures, right? So let me slide this over to the left. All right, so right now an expression is an atomic. So in our thing, a rule is actually the definition of a non-terminal. So this is actually a definition. I think that we should rename this. So let's go ahead and do that. Definition. Let's save it across all those. Okay, and we're going to rename that definition. Okay. Okay, and in their thing, the rule is the expression. So, so I'm going to define this type again. And this expression is going to be I think that we need to keep it open, and then what I mean by that is let's define this stack, leaving out the things that we don't care about yet. But we're going to have alt rule and sequences and prim rules. So this primary, right? So let's open up primary. But you could think, so an expression, the rule, we're gonna do it this. Alt rule is a. I'm very sorry. I'm trying to make sense of this. Okay, so this is the expression. It has only one variant, which is a list of sequences. We could define this as variants of the same type. We could say it's a primary, or it's a sequence of expressions, or it's choice. And this is not sequence, this is a list of expressions. Or it's choice, which is a list of expressions. Now, this will allow us to have choice with a list with a choice in it, which is one of the things that they explicitly remove, right? But I think that this gets us to where we want to be. And now we're going to have to deal with okay, so here this is wrong. What have we got? Yeah, fine. Okay. See, we're at 3 o'clock. Okay. we're going to make a pass, which is going to be expanding character classes. And this is going to take a grammar, and it's going to output a grammar, right? And what we want this to do is to basically eliminate all the character classes. Let's rename that. Okay. So we're going to transform atomic, not atomic, what did we call it? Yeah, we're going to transform terminal with terminal kind of character class. What we want to generate is an expression which is a choice over the elements of the character class. So, and I don't even think that we need to make sure that all the other stuff works yet. I want to get into the nitty gritty of what this does. So let's say expand entry. So this is going to be, and this is going to be a, what do we say? This is going to be a list. List of expressions. Okay. So I have the missing pattern. The single character, this one's going to be simple. So this is going to return just that individual literal string. Okay, so we want and I think that we need the span is grammar span. Okay, because we want to know where it came from. Because we have that in here, right? So we want a terminal, which is, let's fill the labels. The kind is going to be a string, which contains a single character, and copy the span. But that's not an expression. So we have to wrap it in an atomic, which gives us a primary. And primary gives us an expression. Okay, so we can do this across the range of characters. So let's see what the Gleam standard library has for us on this front. UTF code point is an alias for integer, by the way. Um, okay, so if this is a range from a starting character to an ending character, then we need to iterate over that range as integers, right? So we're going to do a little let assert string to UTF code points of start. And this is just, we're using like panic driven stuff here because a pass before this should have checked that there's only one character in each of these ranges, or should have, the parser should have been guaranteed to generate only one character there. Now we could also just say that rather than um, what am I trying to say? Rather than doing it this way, um, we could say that these are integers here, and then we convert them back to code points when we create these literal strings we're trying to match, right? Okay, so what we want to do here is generate um, a list for everything from is inclusive, to is exclusive. Okay, but ranges and character classes are inclusive. Okay, so let's do int range from okay, this doesn't it takes an accumulator. Okay. From start to end plus 1. And then with we'll do use here. This is use accumulator code point. Okay, with the empty list. And it actually doesn't matter. I was going to say we might need to do it in order, but it doesn't matter. They don't have to come out in any particular order. They just have to match. So we will do splat the accumulator, and we're going to do basically what we did above. I could recurse into this, but like there's no point. Okay, so the code point is going to be from UTF code points. Okay. String from, that's the code point. Okay. Oh. Okay. This is got it. It's got to be that this is an opaque type alias or something. um yeah. Thanks for the hearts, by the way. So we've got to do a little bit of stuff here, which is in order to iterate between these, the the challenge here is that this could well, it actually does just those can always be turned into integers, right? Um, the we need to do an let assert okay. This. Um, there is a possibility that someone could specify a range that's not contiguous in the Unicode code point space, right? Like there are gaps that are there intentionally. Um, if they do that, yeah, I want to panic. um, I think it might be nice to um, give a good answer. I don't like better than just this let assert. Um, but I don't know how, I don't need to yuck anybody's yum. Okay, so what we can do here is let's do our first recursive expander. The challenge is that we are going to have to match places where there are expressions. So this is going to generate some garbage, is what I mean to say. Right? So if there's a primary which contains a character class, and I think that probably what we want to do is, yeah, this needs to be self-recursive. Both sequence and choice contain lists of expressions, so those are fine. Before I commit to this, let's look at the other window, which had my original. And there's also this, where's my header file? This. So I think that, right, so this is in reverse order. Okay, yeah, expression is a choice or sequence or a primary. Choice being this struct or record, sequence being that record. Primary is one of these where, so basically a terminal or one of these things. All right, and a choice is a list of sequences or primaries. So this is actually a little bit more specific. So choice cannot contain another choice. This is a thing that we don't need to define in the types, I don't think. But like in a particular IR, we will want to remove the possibility that a sequence can contain another sequence or that a choice can directly contain another choice. Here I just made it impossible in the record definitions, but it's not technically impossible. So we'll want to have, this will be the top level grammar. We'll want to have one that removes redundant choice and sequence such that they can only contain, like we'll define some additional types, right? Where we turn it into ones where those are flattened. Um, and the other thing, I think that there was a bit where a primary could contain, no, a parenthesized expression, which was like this, right? Right now we just have string literals and um, string literals and our character classes and the anything symbol. Okay. Okay, so we're going to this is going to be the tail of our pipeline. And we're going to take g.rules list map, and we're going to say expand character classes rule. Okay, let's import that. Okay, and now we should be able to generate the function. Okay. And yeah, let's rename that def. Okay, so a definition. So we're just kind of going down and narrowing this down. Okay, so for now, expression can only contain grammar atomic. So I'm going to get rid of that, and we're going to go back in the grammar, and this can now be expression. And this is going to break a bunch of things. That's fine. Let's go ahead and generate this function now. Okay, so we're going to match on expression. So for choice, we have this. Right, we just map, we recursively expand those that are inside the choice. And we'll do the same thing here. And we'll read the expressions in there. Okay, for the primary, this is going to be make a new function. The problem potentially here is that we, in the case, let's expand that. Okay, so atomic, we need to be much more specific about this at this level, because our primary, if it's an atomic and it has a specific terminal kind, we need to expand it into a choice, but everything else needs to just return the original, right? Because we don't need to expand that. So let's get in more detail there. So we have terminal. So if it's a kind, and it's specifically a character class, okay, then this is where we'll do our stuff. Otherwise, we're going to return grammar.primary of prim. So on basically unmodified. Now we can inline this function in the bit above, maybe. It might not be necessary. And in fact, it might be better to keep this separate, because if we get something that's not atomic, like as we will eventually, we'll get non-terminals and then like potentially nested rules, depending on how we want to flatten this. We'll want to recurse into that. Okay, except rule in our case is expression. Okay, so now what I want to replace this with is okay, so now we've got a list, and we want to do flat map, right? So we're going to have a list of expressions, and then what we want to return, this is actually way easier than I thought, it's choices. Okay, so let's inline that variable and convert to pipe and convert to pipe. And I like to have pipes on new lines most of the time. Okay, so what did we do? We defined how you expand a character class into a set of single string matchers. And then we recursed into our grammar, and we replaced all character classes with choices over those individual characters. Okay, so I want to write a pretty simple test here. So this folder passes new file, and this is going to be expand our char classes test. Okay, and this is going to be, let's make some tests. And we're going to make another one, which is like single range. And we'll say we might do snapshots for this. We'll see. Ranges and chars. Is that Zed? Yes, I'm using Zed as my editor. I've been using it. Actually, it's funny. I've been streaming on YouTube and Twitch. Quit doing Twitch a while back, but been streaming coding for 3 years, and has it been only 3? Basically, I've been using Zed for just as long. And the reason I picked up Zed, other than I was tired of Emacs being slow for what I needed to do, it was also that my friend Quinn wanted to collaborate with me on one of the streams, and way back 3 years ago, Zed had the live collaboration feature, and Quinn did a bunch of stuff that I didn't see on that stream, and it was really cool. But um, that's yes, I've been using Zed for a long time. Okay, so let's do expanding character classes. So we need to make a grammar. And it's going to have a list of rules, definition rather. We'll just call it class. And this needs an expression. So what I'm going to do is, and I want to abbreviate that because we're going to have to do different IRs. And I'm going to get tired of typing grammar. Okay, so this needs to be a primary of terminal or atomic. Terminal is an atomic, yeah. So primary, what does primary contain? It takes a primary, atomic, terminal. The kind is character class. And here's where the business is. Let me go here and fill labels. Okay. Let's just say span is span. Doesn't mean anything. We're just going to use that. Okay. So this single character, let's say underscore, and single character dash. So some punctuation character class. Let's call this punct. Okay, so what would this look like in the grammar? This would look like you put this in the grammar. Specifically this. That's what that would look like. Okay, so let's do let G2 is expand character classes. Of G1. And then we're going to look at this. So let's go ahead and copy this. This is going to fail, of course, but we're going to change this from so this needs to be a choice. We're going to replace that with choice. So that's the first one. And then dash. So this is what we're expanding to. Why do we care about that? Because what we're trying to do is get this very high level thing and turn it into something lower level that we can we can make efficient. Okay. Okay, so that like obviously we need to deal with this. We're gonna say panic as the problem here is this was expecting to be atomic. And let's do g dot panic is unimplemented. Actually, we can just put to do there. Okay, and now our problem is in our root file. And let's just comment that out. I don't care about warnings at this point. I just want to run that test. Okay, so single range for images of characters is not passed. What other tests do we have? That one's fine. This, let's comment those out. Okay, so we do have, it did pass. So this is exactly what's we expected to be expanded. Okay. So let's do, we're going to copy this just for argument's sake. And then we'll wrap up the stream, I think, because I'm kind of running out of steam and there are other things I need to do today. But let's do character range. And the start is going to be A to B. Right? Okay, so what I want to see is this turns into A and B. Now they may be in a different order, and that's okay. But that's what I want to see. Yeah, and actually they get swapped. And that's because of just putting things on the front versus the back. So if we do that, we should get it passing. Okay. That's good. All right, let's do combination of both. We'll copy this, and this is, we'll say A to B. Is this example. Let's do A to B, and then star plus as options. Okay, so this is going to be A to B, single character, star, single character, plus. Okay, then I would expect to see star and plus. And that worked. Okay. So let's this is going to bail. I think that what we need to do here is do a little expansion here. Eventually, we're going to probably at this level not have the top level grammar. We're going to have an intermediate representation which is simplified, so to speak. So, we got match anything working, right? We've got, now we need to handle you know what? Let's not do that yet. let's not do that yet. I think that um, this demonstrates the thing that we wanted to accomplish, even if we can't lower that into actual Erlang code yet. Um, and there may even be a construct here where rather than building in the top level grammar, we do something like I think it was discussed in the paper if I remember right, like a switch. Um, and let's find it. Da, 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 da. Right. So it's this. So the Pappy's optimizer uses an internal switch operator. It can't be invoked directly. So like we would create this switch thing, um, only generating through the left factoring optimization. The other thing that we would do here is we would define the character classes in terms of this switch operator. Um, so our expansion would be turning this character class operation into the switch operator. Um, yeah. Mm, right, and there's bits here. We'll talk about memoization later. Um, virtual inlining are things where uh, you look at the cost of a particular rule and you go, is this worth memoizing? Um, and that kind of has to do with some heuristics about like how much do you want to consume and like how expensive is it to match that particular thing. Um, so we'll get to there. Um, their thing is built around self-recursive data structures that are lazy. We don't have access to in Gleam, so we're not going to bother with that stuff. Um, but yeah, this switch operator basically turns into this sort of thing as you would expect. Okay, I think this is a good place to make a commit and end for the day. So let's look here. Okay. Right, so at this point we should have expanded character classes. But what we could do also is eliminate that with the type definitions. So we don't have to panic there. Okay. So episode 2, match anything operator and expand character classes into alternatives over their members. Now, if we in the future support regular expressions directly, I don't know that I want to in this new version, but we may have to keep the regular expression as sort of a primitive operation um, rather than doing this expansion. I think that there's some potential value in still doing the expansion of character class stuff into um, individual results. Okay, that's going to be it for today. I'm gonna publish this branch, push things up, and we will continue next week with more exploration of this space of generating code and optimizing it and so forth. So thanks for